Okay, today we are talking about thrust, energy, and work, and how it relates to the ideal propeller. Now, the ideal propeller creates uniform rectilinear motion. That means the same velocity coming out of the propeller at all points and all going in the same direction. Here's non-uniform motion, and here's non-rectilinear motion. So, using the thrust equation, where the force of the propeller equals the m dot times delta v, and delta v is the change in velocity, or the final velocity coming out of the propeller, minus the initial velocity going into the propeller, which is the speed of the ship, because as the ship moves, from the perspective of the propeller, the water is moving into the propeller. So, we find m dot, which is mass divided by time, to be area times rho times the final velocity. And we write it as follows, or more simplified here. Now, to calculate the energy to create this thrust, we have to find the initial energy and the final energy. And this would be, the initial energy is 1/2 m times the initial velocity squared, and the final energy is 1/2 m times the final velocity squared. Now, dividing the energy by time gives us power, and dividing time by the opposite side of the equation turns m into m dot. And we can plug in what we found for m dot before, area times rho times the final velocity, and multiply that to the equation to get the power more simplified. So we take area and rho and bring it outside, and we multiply the final velocity by both of these terms to get 1/2 the final velocity cubed minus 1/2 the final velocity times the initial velocity squared. And this is the power required to generate this thrust. Now, to calculate the work. Work is force times distance. And the power is work divided by time. Now, this power is the power that actually gets into the vehicle, not the power of the propeller. And so this is force times VI, or the speed of the ship. Now, we can also introduce the force of drag on the ship, which is K, a geometric constant, times rho, times the velocity squared, the velocity of the ship. And we subtract that drag from the force we found earlier. This is the force of the propeller, and this is the drag force. And we multiply this entire force by the velocity of the ship to get the power. And the power simplifies to this equation here. Now, using these equations we've derived, here is an example. A ship propeller pushes water out the back of the propeller with a delta V of 15 meters per second. And the ship moves at a speed of 10 meters per second. The area of the propeller is 0.5 meters squared, and the density of the water is 1,000 kilograms per meter cubed. Using the equations derived earlier, calculate the power of the propeller and calculate K if the ship is traveling at its terminal velocity. I will make another video explaining the solution to this example.